So, we will continue with this video course on electronic systems packaging. As you can recollect, we have seen the following chapters: Introduction to Systems Packaging, Semiconductor Packaging Overview and Fundamentals, all about packages, overview, different types of packages, advanced packages, and the salient features of various types of packages we have seen. We have seen electrical design issues in packaging, and we have also seen computer aided design for printed wiring boards, typically system level printed wiring boards, and concepts like design for manufacturability, design for reliability, design for testability, and so on. Now, having completed these chapters, it is now time for us to go into the technology aspects of system level printed wiring boards. I emphasize here that we are talking about system level printed wiring boards. We are not talking about printed wiring boards that are really low dense, but along the way we are going to see manufacture and technological aspects of all types of single, double and multi-layer boards, including high density interconnect organic substrates that are used for advanced packages, as well as for mounting these advanced packages, multi-chip modules, etc., onto a basic substrate, typically an organic substrate. When we talk about printed wiring boards, we think about organic substrates. There are of course ceramic boards which can be used to mount packages and interconnect them. Before we go into the technology aspects of printed wiring boards, as a last review, we will look at the CAD process steps only by illustrations. So, this is something like a quick review, not exactly a tutorial, but a quick recollect of what we have seen in the CAD. I will reduce the explanations here as much as possible, but you can have a look at the basic illustrations, and this will explain to you the complete process steps that normally one encounters in any CAD program. So, I hope this will help all of you into the confirmation of what exactly needs to be done if you work with a CAD package in terms of process steps, in terms of the deliverables, in terms of the outputs that you can generate for a manufacturing process. So, that is the aim of this review illustrations. So, we will start this review. The first thing in any CAD process is the electrical component selection. Components that will be used in the electrical schematic are selected and designed. So, as you can see here, you can create a symbol and you can create a equivalent footprint, because this is going to be used in the electrical schematic page. We have seen what is a schematic. The electrical components are placed in the schematic screen and the net connections are established. So, you can have about 100 components placed, actives and passives, and they are interconnected. So, that will complete the schematic part of the CAD program. So, as you can see, IEEE symbols are used, various passive devices are used, and then they are interconnected. Then the bill of materials is automatically generated from the library, because the library will contain details of the components that exist in the schematic in terms of what is the part number, what is the reference designation, what is the format or form size, then the part number and the company from where it has been purchased, and you can also link it to the data sheet of that particular device for instructions on mechanical footprints and so on. So, bill of materials is a very important thing in the documentation part of a CAD work. PCB component development. The components that reside on the PCB are designed from the bill of materials. These PCB library parts are captured in the netlist. As you know from the schematic, you are generating a netlist, and this netlist is used with all the information about the component, the footprint and so on, and is used in the layout as well as the routing stage. So, this figure that you see here includes the component development aspect, footprint development aspect, and that is embedded in the netlist. So, the netlist will look like this. We have seen in the earlier class what typically a netlist will do. A netlist is very important if you want to export your work to some other CAD program. So, the netlist is typically an ASCII format file generated from the schematic. It contains all component and connection details, that is the part and the net information required for the PCB design. Then you do a netlist verification. So, as you can see in this figure, there is what is known as the rat's nest. The components are dumped on the screen in the layout module of your package with the connections. The yellow lines that you see here are the netlist connections. So, this is typically a medium dense or high dense package design that you see here. You can see various parts and the crisscross connections between the components. So, this is the output of a netlist. Now, you can see you can switch off the net in your software package and look at the total number of components that have been used, that means the footprint details that have been used in your design. So, components from the netlist are dispersed and grouped. So, here as I mentioned before, you have to use your skills to manually place the components inside the PCB outline, at least 10 to 20% of them, and then probably you can go in for a assisted placement. Now, components are placed within the PCB board outline. So, the board outline definition is a key factor in deciding the product size. Keep outs, cutouts and holes, mechanical holes other than the electrical interconnect holes that you may use for your electrical circuit needs to be created. So, normally you will have mounting holes, sometimes you may have to create some kind of a opening for placing a mechanical component in the board outline itself, but these can be avoided by a better design. Then we go to the routing program. Utilize the routing efficiency of your CAD program to interconnect the components based on the netlist information that you have generated. All connections or nets require trace routing. The red lines, as you can see here in this particular figure, are completed trace connections. The yellow lines represent unrouted or incomplete traces or nets. Plain connections are created with a via or direct connection to a copper area that you have generated for ground and so on. Trace routing may consist of component to component or component to plane connections. So, unrouted nets can be done manually, or you can do a better placement procedure, or you can also modify the design rules and then complete the routing for your design. There is always a possibility that you may have to pour copper in your design. Okay. When is copper used? Copper areas are created, the red areas that you see here, and poured over vias, the white circles that you see here in this figure, and solder pads. Okay. So, these are the solder pads. Copper areas are then assigned at net name that matches with the appropriate net connection. So, this is a very important period in your electrical design, where you assign the area or the copper pore area that you decide for your electrical circuit performance, and sometimes the traces end with the copper. Okay. So, this will act as ground areas, and these are very essential in a multilayer board. This is the plane of a PCB design. The copper planes are created, split and defined according to the design rules and net requirements for each layer. Thermal and non-thermal connections are placed accordingly. Sometimes the copper can act as a heat sink, and therefore, vias can end in a plane. So, it requires the creativity of a designer to put this copper plane areas in the inner layer of a multilayer board and assign the tracks or lead the tracks to the plane. So, the via connections need to be decided in terms of the via size and so on, the plating for the vias, whether it should be an anti-pad connection or it should be a thermal relief connection for thermal purposes and so on. Design for testability, I have talked about this earlier. Design for test involves placement of test points into the PCB. So, you have to decide what types of test points you should have. One is a in circuit testing and the other is a flying probe test. So, if it is going to be an equipment based, then your placement has to be accordingly well suited for accessibility to your flying probe tester. DFT analysis is executed and test points are audited for compliance and testability. Verification of the electrical circuit is an important requirement. The PCB is complete at the CAD stage and must be verified for the design rules whether they have compliance or not. Verification includes clearance check in terms of, let us say, via to via clearance, via to pad clearance, pad to pad, pad to track, track to track, track to edge clearance and so on. Net and copper plane connectivity, duplicate nets, layer to layer connectivity if it is a multilayer board, design rule violations that you have to periodically check based on your design rules, design for manufacturability and test points. Then you create the Gerber files. So, Gerber files are created to enable plotting of the individual design file elements that you have completed. Depending on their function, each Gerber file is compiled as an individual electrical layer, process or design reference. So, what are the areas in which you can create a Gerber file? As we have seen earlier, you can create electrical design layers. It can be multiple layers, layer 1, 2, 3, 4 for a multi-layer 4-layer multi-layer board. Silk screen legend areas, legend layer, solder mask layer, it could be top solder mask, bottom solder mask, solder paste that is required for surface mount assembly technology, fabrication drawings documentation, assembly drawing documentation, aperture files, or you can call it as D codes that is used for similar to your Gerber file, that is used for looking at the pad openings, pad sizes for your electrical layers. You can also create drill files, okay, that needs to go for manufacturing, net list and XY placement data for assembly. Gerber files are processed to create each electrical layer, internal and external both, that will ultimately be finished in copper on the PCB. So, this is an example you see of a plotted Gerber file for a particular electrical layer. You can create multiple electrical layers. Now, this is an example of a visual capture on a screen of a silk screen legend Gerber file. This file will create the stencil that will be used to apply silk screen printing, that is an ink that is used to the PCB. So, this is basically a text information that will tell you where the component is located or need to be placed, identification of a component and labeling, proper labeling of the PCB. So, this silk screen legend text exists on the outer layers. You do not have to do it for the inner layers, because there is no component in the inner layers. You can create a solder mask Gerber file which will expose solderable areas only and protect the other areas of the PCB by using a epoxy ink. We have seen this in one of the earlier classes. So, for that you have to create a mask. This is again done by printing process or other advanced methods like dry film methodology or a curtain coating methodology is also available. The solder mask utility minimizes solder bridging between components, because it protects the entire PCB except the pad areas. So, in this example the Gerber file is created as a negative. Areas in red that you see here will not be covered with the mask. The other areas will be covered with the solder mask. The solder mask exists on the outer layers only. So, needless to say, solder mask will be applied only on the top and bottom layers of a printed wiring board, not the inner layers. This is the file that is used to create a solder paste mask Gerber file for solder paste printing. Solder paste printing is a methodology that will be used for mounting surface mount components after the board is complete. So, instead of this is one of the method for assembling surface mount components. So, we will get to know about this when we talk about surface mount technology, but it will be better to know that as a designer you can also create this solder paste Gerber file. So, you can see the openings here, that is the surface pad areas of all the components, on top of which your solder paste will be printed, or it can also be syringe dispensed in very minute volumes, and on top of which the surface mount components will be placed, and then it will be sent for reflow soldering, and that is how the attachment takes place of the surface mount devices onto the surface of this board. What you see here in this figure is an assembly drawing, which is an important document that is required for any process of fabricating a PCB, which requires future reference. It basically gives you the location of the components, and importantly it will give you the orientation of the electronic components that is used. It will also give you an idea that if you do too much of experimentation with the orientation, you will end up with a poor design, a poor manufacturing yield. Okay. What you see here now is an aperture listing called the D codes. So, the D codes are basically a listing of the various pads that are used in the particular layer. So, the photoplotter that is used for this mask preparation will read this aperture listing, and the aperture in the light source of the photoplotter will open the aperture according to the dimensions mentioned in this list. So, this is the utility of this aperture listing. Then you can create drill files, as I said. Basically it contains XY coordinates. It will also list the number of drill bits used in this particular design for drilling, and for example, if you have 0.5 mm drill bit, what is the number of holes that need to be used with this particular 0.5 mm drill bit, and so on. So, this is a manufacturing requirement, and this data is fed to the CNC drilling machine. So, that completes the Gerber file requirement that you will be able to create once you finish your CAD work, and now the board goes for PCB fabrication. So, as we have seen earlier, PCBs or printed circuit boards or printed wiring boards comprise a rigid sheet of epoxy impregnated fiberglass material within copper sheets affixed to one or both sides. So, you can have a single sided copper, double sided copper, and therefore, it is known as a copper clad laminate. In multi-layer boards, those with more than 2 copper layers, a piece of material called pre-preg is placed between the core layers. So, if you can see in this particular figure, this is an example of a multi-layer board. What you are seeing is a cross section. There is a basic core that is used. This is the core, and then we have the dielectric pre-preg material. This is the pre-preg. Then you can have another pre-preg here, and then the copper is built around this, okay, and that is how you create copper layers in the inner layer of a multi-layer structure. And this is the via that is used to interconnect the copper layers. This is also a via. This is plated, therefore, it is known as a plated through hole structure, and you can have your ground and VCC layers well designated in this multi-layer, and these can be connected to the top or the bottom electrical layers through the vias. So, now with this background in mind, we will enter the chapter on printed wiring board technologies. So, what we intend to cover in this is all the basic fundamentals of printed wiring board technology, the fabrication, the materials, the simple processes that make a combination of an extended process called a plated through hole process, and those that require high density interconnects. Therefore, we are going to start from a simple printed wiring board manufacture for a single sided board to the current technologies that exist for high density interconnect substrates. Now, we talked about Gerber files. The Gerber files is actually sent to a place. If you have in your own institution a photoplotter, it can be fed to the photoplotter and you can create the mask. Otherwise, you have to look for a vendor who will create this photo tool or a mask and then give it to you, or sometimes the manufacturer has this photoplotter which will be in a clean room area, because you are going to handle very sensitive materials like the photofilms, and then this mask, whether it is a single layer or a multi-layer electrical layers, and then as I said, all the various other utilities like a solder mask layer, a legend layer and so on can be generated with the photoplotter. So, we will begin with understanding what is a photo tool. So, I will use the term mask or a photo tool interchangeably, both mean the same, different people use different notations. Artwork is basically was used when manual taping was done as a means to generate the electrical layers. Those methods are obsolete. So, you can call photo master, that is your photo tool can be a photo master if you want to preserve it for a long time, and if you can use some thick polyolefin layers to generate your mask, and from the photo master actually you can create a photo tool. The photo tool or the mask is basically used for actual handling and fabricating the PCBs. It is used in the workshop floor of a printed wiring board industry. So, it is very convenient to use the term mask or a photo tool. Now, this photo tool is a result of a CAD output in a Gerber format. It is a universal format. So, basically the photoplotter will have a light source. It will have a light source and it will have an XY table. Now, on this XY table you are going to place your silver halide film, and then your light source is going to interact with the silver halide material based on, as I said, the decode listing, right. We talked about the decode aperture listing. So, this will be used by the Gerber equipment to resolve where the pads are going to be placed, what is the size of the pad, and it will also draw the lines that connect between pads and the vias and so on. So, basically it is an activity where you will see an XY movement of a table on a table with the light source hitting the actual intensity that is required to react with the thin layer of the silver halide that is present on a plastic film. Now, the manufacturer can scan, he can edit your Gerber files if required, but mostly they scan and look for errors, look for compatibility in manufacturing, look for DFM rules that cannot be met, and they will interact with you if they want to change some of the parameters or features. For example, it could be some net which is very small enough which they can probably not manufacture, and therefore, they will ask your permission to modify that. So, you have to be careful with the editing of the Gerber files. Now, photoplotting equipment comes in either a raster format or a vector format, but today most photoplotting equipments are raster and laser based. The initial photoplotting equipment that came into the market was mostly vector photoplotters. Vector photoplotters basically are very slow. So, what it basically does is it opens the decode of a particular value. Okay, let us say it is 40 mil pad that is listed in your decode. It will finish all the 40 mil openings in your entire design before closing that aperture and moving to the next pad size. So, it is basically time consuming, tedious, and typically for a 100 by 160 mm photoplot file it would take almost 2 hours, but today the same size you can do it in less than 15 minutes because of the raster technology that you normally see in your laser printer. Okay. So, the printing is basically from top to bottom, right, left to right, and so on. So, it is basically grabbing the information and doing a quick plotting using raster technology. Now, the silver halide film is the important component that is used to provide or produce your masks, and they come in two different sizes, 4 mil and 7 mil. 4 mil is basically 100 microns and 7 mil is 175 microns. So, typically for a photomaster you will use a 7 mil film and preserve it, and from the 7 mil you can create a 4 mil photo tool or a mask that can be used in the manufacture. Once you feel that the 4 mil film has been damaged or it has lost its dimensional tightness as you call it, then you can make another photo tool from the photomaster. That is the advantage of using the thick and the thin silver halide films. Then once the exposure is done to the silver halide film, you will have to do a photographic process, which is a regular photographic process, but today you see we are all using digital cameras. In the earlier times we were using photographic film inside a camera, you expose it and then you develop it using a photographic process. Okay. It is a 3-step photographic process. Now, that is totally stopped in the commercial aspect. You see most of us use digital cameras and directly we take the positive prints. So, earlier we used to go through the process of creating a negative, and from the negative we take a positive print. So, but this mask generation is a direct printing, whether you want a positive print or a negative print you can do using a photoplotter, but the photographic process has to be undergone because you are going to create a very stable silver halide photographic film. and then once the chemical process is over, you do a stabilization of the film before it can be used in the workshop floor. Now, what you can see here is a photo plotted film. This is called the photo tool. It is a very delicate body. On the left side, you see in this particular slide, you are seeing a positive mask, and on the right side you see a negative mask. What is the difference? In the positive mask, the circuit areas are black. In the negative mask, the circuit areas are open. Okay. So, basically the requirement of using a positive or a negative depends on the PCB process sequence that you have designated for a particular board. We will exactly see when to use a positive mask, when to use a negative mask, but the left one you see here is basically black areas are circuit areas, the transparent areas are non-circuit areas. Here you can see on the right side, transparent areas are circuit areas, and the amber color area, which actually is not a silver halide film here, is the non-circuit area. Okay. So, this has got a lot to do with the process steps. Now, if the photo tool is good, then your board is good. If your photo tool is bad in terms of very poor contrast or broken lines or not well defined images, then your PCB is going to be the same, because it is going to be a replica that you are going to transfer from the mask to the copper surface. So, make sure that you do enough quality control when you are creating masks. If you can look at this sample here, what I have basically shown here is, on this side you see this is the positive photo tool. So, this is the positive photo tool, and here you see this is the negative photo tool. The color difference here is basically, this is a diazo film, whereas this is a silver halide film. So, I am now going to explain to you what is the difference between a diazo film and a silver halide film, when to use each of these. Now, a typical photo plotting equipment, if you buy or if you look at the specifications, most of what I have listed here will be there. If you look at the figure that I have used here, basically there will be an XY table, what you have seen here. A film will be placed here on the XY table, and the equipment will have all the optics, because there is a light source, and the optics has to collimate this light with a particular intensity and wavelength onto the film. Okay. That is very important. So, the distance between the XY table and the light source or the lens is very important. Okay. Now, there will be an aperture wheel which will open the apertures according to the D codes that is found in your aperture listing from the CAD data. Now, typically in a vector plotter, one of the apertures will be open, and all the XY coordinates where this particular aperture is used, the exposure will be completed. Whereas, in a laser vector photo plotter, as you can see here, here also there is a light source. Okay. Now, basically because of the raster format, you will see irrespective of the D codes, they move very fast and the apertures are open very fast enough, and basically you are not looking at sequential operation, you are looking at the complete film, and the laser photo plotter and the laser source is so sharp that you can do this entire operation much faster than the vector. Of course, the light source used here earlier was different compared to the light source that we are using nowadays. Now, basically there will be a photo plot on silver halide films. You can use 4 mil or 7 mil films, but 7 mil is preferred because the dimensional stability of 175 micron film is preferred. because you might use this in the workshop floor. It will be exposed to various factors like humidity, dust, temperature variations in the exposure equipment and so on. Gerber files are the input data. AutoCAD drawings can be accepted if you want to use some mechanical drawings and then make a mask. Lithographic film is used. Okay. So, that is why it is called lith film. Large film sizes are used in the equipment like 32 inches by 28 inches. So, you can have multiple plots. Multiple plots can be generated on the film, and each film can accommodate various designs. Okay. So, you do not have to waste the photographic film. Now, there will be usually drums, vacuum drums that will hold these films. Okay. So, there is no air gap between the film and the XY table, and also if there is an air gap, you can expect a variation in contrast in the image. So, the vacuum hold is very important for these films. Multiple plots can be done. Plots can be fitted to PCB panel size. That means, the entire plotting that you do here can replicate the PCB. So, this has a lot to do with understanding the manufacturing capability in a particular company. So, plating capability for a large size and then all the other sub processes that we are going to see, whether it can be done in large area is a issue. Now, scanning and editing of text files is possible. Chemical processing follows plotting process. Stabilization needs to be done after the plotting is over, after the chemical process is over, and the stabilization time is usually 4 to 6 hours. Okay. In controlled conditions in the lab, typically where temperatures can be around 21 degrees centigrade, 55% relative humidity, so that the film can stabilize, and only after stabilization you give it to the manufacturing. Typical raster photoplotters can cost anywhere from 50 to 1 crore. Okay. So, that depends on the range and the capability and the resolution, okay, and the accuracies that and the smaller line widths that can be used. Resolution as high as 40,000 dpi. Accuracy or the positioning part of it is plus or minus 2 to 4 microns. Today equipments are available. Minimum line width, typically people require 1 mil, that is 25 micron, but very expensive, but most machines offer 50 micron minimum line width. You can directly create negative and positive masks. Other masks for solder mask and silk screen can be generated. You have to use red or mild green safe lights for loading the photographic film, because otherwise if you have white light, the material will be exposed to white light and then the material will be degraded. So, you have to use the recommended red safe light in the lab where you are using the photoplotting equipment, and this continues for loading the film and until the photographic chemical process is complete. The data transfer protocol is typically Gerber RS274X. Now, what about the light sources? There are different light sources that are being used. Earlier people were using xenon, LCD image projection technology is also being used, laser direct imaging is used today, highly accepted. Initially it was not cost effective, but today with more volumes being used, it is becoming affordable. Now, if you want to use laser direct imaging, you have to use a compatible photoresist material. So, this is in short what all you can expect from a photoplotting equipment. Now, we talked about the photofilm that is used in the photoplotter. What is the structure of a photofilm? So, basically it contains active silver halide. Okay. So, this is the most important thing that you will have to look for. There will be an emulsion which contains the silver halide in a gelatin format. Now, you have to protect it till it is being used. So, there will be a protective layer. Then there are some sub layers where you are using some adhesive, because your base polyester film needs to adhere to your emulsion layer. Even the protective layer needs to be carefully adhered to the emulsion layer till all the handling of the photofilm is complete during its process. So, there will be a polyester base and there will be sub layers, okay, there will be other backing layers, and finally, there will be some embedded light absorbing materials, because as you know this is a catalytic reaction, right. So, light source falls on the sensitive areas of your photofilm, which is basically the silver halide material, the grains of silver halide. Now, what is a silver halide? Silver halide. So, it can be a chloride, bromide or iodide, but typically iodides are not used, chlorides and bromides are used in the photographic industry, right. The thickness, as I mentioned earlier, can be 100 micron, that is 4 mils, or 175 micron thicknesses, that is a standard. Now, I was talking about the light source falling on this film in the actual process of the photographic process or the photo plotting. What basically is required is there should be some light absorbing materials which will start a catalytic reaction, right. So, this process has to propagate through the entire material, silver halide material, that is embedded in gelatin and that is very uniformly spread in your photographic film. So, this will cause changes chemically and physically also, you will see changes in the color. So, that is the basic chemical process that you are seeing when you have the light exposed in the photoplotter to the silver halide film. Now, silver halide photo tool, like the mask that you are seeing here, you have to handle very carefully, okay, because you cannot afford to have defects. You must have a defect free photo tool. What are the defects you can see? You can see pinholes, scratches, lift off flakes, inadequate contrast between the black and the white areas. So, if you want a good resolution when you do a photo imaging onto the PCB, the black and white areas in your mask should have very good contrast. That depends on the photographic chemical process that you are going to do. And flatness, you should have very good flat surface. So, make sure that there are no dents. Okay. So, one of the defects can be sometimes you can see there is no flatness, there is warpage, or there is some kind of a bend or a sharp corner due to bending and so on. So, identify if any of these defects are there, and if any of these defects are there, they cannot be used for the manufacturing, because these defects will get transferred as it is in terms of copper onto the PCB. Okay. So, the success of handling a photo tool is very important, because it directly depends on the success story of your PCB manufacturing. Now, the silver halide film can be transferred into a diazo film. That is the trend today. People are not using silver halide film directly, people are converting it into diazo films, which I just showed you in the sample. That is used in the shop floor. So, what is the photographic chemical process that one will actually have to do once the exposure in the photo plotting is done? So, basically the photo plotter does only light source exposure. After that is complete, you can say that the photo plotting process is complete. Then the film is unloaded from the photo plotter and then it goes for a developing process. Now, in the developing process, which is a chemical process, you have a developer solution. What is the developer solution? Typically, it is called hydroquinone or metol commercially. These are commercially available chemicals, and this is the one that is recommended by the manufacturer of the silver halide films. In this particular process, you are making the latent image visible. So, if you take the exposed film and if you are going to insert it into a photo developer, you will see that the process taking place, this conversion of the dark areas coming up onto the film can be visibly seen. Okay? That is how you are seeing the latent image made visible. Once the exposure is done, there is an image which you cannot see. Now, you are making it visible by doing this developing process. What it basically does is reduces the silver halide to metallic silver. It is a reduction reaction, and that is what is expected from the developer. Time and agitation of the developer bath is very important. Therefore, you have to look at the concentration of the solution to achieve a very good developing process. Orthochromatic or lith films are used. Commercial term is lith. Then you have to use safe lights. Once the latent image is made visible, you can stop the reaction at any point of time using a stopper bath. It is basically a 1% acetic acid solution. You can take out the film. If you can really read at that point of time that the developing process is complete, you can stop the reaction, or if you want the developing process to continue for some more time, you can put it back into the developer solution, but such allowances are not acceptable. These are timed process cycles. You have to be very careful with the timing process, because this is a very quick process. Typically, a developing process will be over within 90 seconds. Okay? And again, that depends on the stability of the developer bath. Time is very important, agitation is important, and the concentration of the solution is important. Then once it is complete, you can put it into a fixer bath. The fixer bath, the capability of fixer bath is that it permanently fixes the image. So, what you see here in this film, you cannot do any damage to the circuit areas here, okay, unless you take a knife and scratch out the black areas. This is a very permanent image, very stable image. It has stabilized well. So, the fixer bath will create this kind of a permanent image. Okay. After that is done, before that the fixer bath chemical is typically sodium thiosulfate. Now, the concentration depends on the suggestions given by the manufacturer. Of course, you have, if you have experience with this process, you can work with these concentrations. Then you can wash, dry and stabilize the film. Dimensional stability is required. And now, the diazo film that you see here. So, this particular film, what you see here, comes from a typical developer fixer chemical process. But whereas a diazo film that you see here, which is amber in color, does not go through this process cycle. Now, the former one is a wet process, whereas this one is a dry process. I will explain to you how a diazo is obtained. Diazo films are basically a film, a plastic material, a polyolefin plastic material that is coated with a diazo compound. Okay, it is an organic compound, it is a diazo compound that does not require the chemical process that we have seen just now. It basically utilizes a dry developing process using ammonia. So, once the exposure is done in the camera or in the photoplotter equipment, or basically you can do a 1-to-1 contact of your positive or your negative image, and you can do a simple light exposure using UV light to the diazo film. Okay. It is basically a duplicating process. Then you can take the film and dip it in dry ammonia for a couple of minutes, and you can see the amber color coming up. So, basically there is a different set of reaction that takes place between the diazo compound and the ammonia. Now, the advantage is that the amber color that you see in this film also cuts off UV light, just as the black area in the normal silver halide film cuts off UV light. The amber color also cuts off UV light, with the advantage of the amber color providing better visibility for us to do registration between this mask and your printed wiring board. Okay. So, that is the advantage of using diazo film. It is thick, it is 175 microns thick, and it can be handled easily, and you can make as many duplicates as you want. Okay. Suppose if you have done with 2000 boards, and if you feel there is a dimensional problem with this film, you can throw this and make another diazo film very quickly. So, exposed areas turn amber color on ammonia exposure. It does cut off UV light just as black silver halide does, therefore, you can do better registration. Available as 7 mil film only, therefore, better handling in shop floor, and can be used for making multiple copies to avoid errors that we have seen, like a pinhole or a flake or a dust sitting on the areas, tracks which are very small, and so on. So, this completes the manufacture of masks, or the developing process, dry developing, wet developing process for creating photographic tools, photo tools or masks. Now, we will proceed into basic steps in the manufacture of a single sided board. We start with a design, right. We have completed the design, we have seen what a photo tooling process is. So, basically here you have to concentrate on creating a 1:1 image that will go directly onto your copper board PCB. The next step is you image or print this image onto your copper surface of your printed wiring board or copper clad laminate. Then once the imaging is done, you etch out unwanted copper. Etching is a process where you can remove any metal. You can etch a metal, you can etch a plastic, you can etch different metals with different etchants, or inversely a particular metal will have to be carefully removed by using a selective etchant. So, in this case of copper, you have to use selectively etchants that will remove copper from the surface of the board. Drill holes for component mounting for your through hole components, protect the copper and thereafter the solder material. Okay. So, basically you are first protecting the copper with solder, and then the entire board is protected with a solder mask, and then finally it goes for assembly. So, it can be your typically in this particular process cycle, it is a PTH assembly, because we are talking about drilling holes for component mounting. In the case of surface mount technology, you do not require drills for mounting your surface mount devices. Then we go for a double side manufacturing process. Here the process steps are design, photo tooling, that is you create a 1:1 tool. Now, the drilling of the holes becomes of prime importance, okay, because you have to connect the two sides of the printed wiring board. So, basically you talk about a 2-layer manufacture. Therefore, you will have a copper layer on top, copper layer on bottom, you have to interconnect them. Therefore, the drilling of the holes becomes very important and providing interconnection between layer 1 and layer 2. Plate using electrolysis process first the holes and the hole wall, image the circuit using the mask that you have created, plate with electroplating copper, plate tin or tin lead with electroplating process, remove the photoresist or the mask that you have used, then etch out unwanted copper, and finally strip the photoresist or the mask again, and then protect your board with solder mask and finish the entire process. So, this is a very simple listing of the single and double sided process. We are going to look into much details of all the processes that make up the entire process sequence. This will be discussed in the next class.